In this section, we're going to look at electric current and circuits. An electric circuit is any complete conducting pathway. So let's say we look at a simple circuit. A simple circuit has a battery or some kind of power source, and usually to show what that looks like, we would use two lines, one a little bit longer than the other, because the longer one represents positive and the shorter one represents negative. Then you need some kind of load in the circuit. So for this particular example, I've used a resistor, and you connect it back to the original point, which is, say, the battery or the power source. Now, an electric circuit always flows from high voltage to low voltage. What that means is on this particular side, we actually have a high voltage, let's say 6 volts, and then on the other side, we would have 0 volts. That way it flows from one side to the other, so in other words, it goes in this particular direction. Current will only flow when a circuit is in a closed loop from one terminal to the other. So in the example I've shown you up the top, you can see it connects all the way from the start to the end with no breaks in between, and that way this current will actually flow. So what is electric current? Electric current is the movement of charged particles from one place to another. Now, you can only get current if you have a difference in charge. As we saw from before, we have high voltage to low voltage. If you have one being positive and one being negative, that will also work. So for a current to exist, there must exist a net movement of charge moving in one direction. A metal conductor does not have any current flow, even though there are electron movements within, as it does not have electrons moving in a uniform direction. So please keep that in mind. Electron currents will only flow in one single direction. Now, you might have noticed on the diagram I showed you before, so I'll draw it again. It looks like this. Has a circuit that goes through. I wrote down that if you have a positive to a negative, it goes in that particular direction. This is actually called conventional current. Now, why is it called conventional current? Well, if you think about it, usually we always say the electrons are the ones that move, not the protons. However, you might notice on this particular diagram, it goes from the positive side to the negative side. That means we're saying the protons are the ones that are moving, not the electrons. However, in reality, we know it's actually the other way around, because we know the electrons are the ones that move. So in reality, it actually goes in this direction. And this is called the electron current. Now, why do we use conventional current whenever we draw diagrams? That's because back in the day, people used to have, people didn't know which one was the one that was moving. They all just kind of went, okay, well, protons must be the ones that move. They just set one of them that moves, and so they drew all the diagrams that move that way. Obviously, upon testing and improvements in technology, people found out that it was actually the currents that move, the electrons that move to cause the current. Well, to be honest, we just set it whichever way we want anyway. We just call one thing being a proton, one thing being an electron. We can always just reverse it and just say the diagram's still right, as long as we reverse it. So usually we just leave it as conventional current. So just keep that in mind. Whenever we are drawing diagrams, we are actually drawing conventional current. We do not use electric current in diagrams. You also have extra current movements. You have two types. You have what's known as direct current, so it only flows in one direction, or you have what's known as an alternating current, where it flows in both directions. Now, why do these exist? If you have a look here, batteries only flow in one direction, so that's called direct current because it only flows in one direction. Alternating current flows in both directions. The reason why alternating current flows in both directions is because of how a battery works. When a battery generates electricity, what you need are three different things. You need a force, you need a magnetic field, and you have electricity. So if you have two things, you will always generate the last one. So for example, if you have force and electricity, you would generate a magnetic field. If you have magnetic field and force, you would generate electricity. So obviously in this particular case, we're looking at force and magnetic field generating electricity. So what that means is you have a motor. I don't know what a motor looks like. There you go. There's a motor. You have a magnetic field, north, south, like so. We force it so it moves. That way it generates electricity. However, you'll learn this a little bit more when you get to year 12. Whenever you generate electricity, the magnetic field actually fluctuates because you actually have a switch in the magnetic field once it rotates past a certain point. When you actually have a switch in magnetic field, that also switches the electricity because the electricity depends on how the magnetic field is set up. So if you have a look at the diagram here, the force always goes in one direction. The magnetic field switches, so it goes in both directions. If it goes in both directions, and it must be equal, that must mean the electricity goes in both directions. That is why alternating current always goes back and forth, just so that you're aware. Alright, so for most of year 11, we are only going to look at direct current whenever we are doing calculations. So what that means is we are looking at current which flows in one direction only. And because we simplified it in doing so, we can use this formula here, which talks about current. So please write this down. The current of a circuit is determined by the number of electrons that passes through a point, because remember we said current is how many electrons passes through a point in a certain amount of time, and so it becomes the number of coulombs over time. Now, in real life scenarios, we normally use milliamps more than amps because objects usually have really high resistances. I'll come back to that when we talk about resistance. But just keep in mind, in real life scenarios, we usually use milliamps, not amps. And just as a reminder, milli means 10 to the power negative 3 or 0.001. I think I counted that right. 1, 2, 3. Yep. Okay. What is the current in a conductor if 10 coulombs of charge passes through a point in 5 seconds? So, current is the number of charges over time. So we have 10 coulombs over 5 seconds. That gives us 2 amps. How much charge passes through a point? Passes through a load if a current of 3 amps flows for 5 minutes and 20 seconds. So, rearranging the formula, we have I equals Q over T. So this is a divide, so we times the T onto the top. We get Q equals to I T. That's 3 amps. And then we have 5 minutes and 20 seconds. Remember, time always has to be in seconds. So 5 times 60 to give us back 5 minutes and seconds. And then we have another 20 seconds. That's 3 times 320 seconds. That gives us 960 coulombs. Calculate the number of electrons that flow past a particular point each second in a current that carries a current of 0.5 amps. Sorry, I misread. In a circuit that carries a current of 0.5 amps. So Same thing as before, we rearrange it already. Q equals to IT. That's 0.5 amps, and we have 1 second, so that's 0.5 coulombs. So the number of electrons would then be 0.5 coulombs, and remember we need to divide it to find the number of electrons. The number was 1.6 times 10 to the power negative 19. Putting that together, we get 3.12 times 10 to the power 18 electrons. Now, you might ask the question, why did I not use the negative part here for the electrons? I should, or I guess I can, but remember, in a real life circuit, current flow is going to be the electrons moving. That actually means this is also negative, so negatives cancel.